introduce myself. My name is Aurelia. I'm head of events here at EHPA, the European Heat Pump Association, which is one of the partners involved in this Interreg North Sea projects. And I'll be your host today by moderating this very short 45 minutes webinar. Thank you again for being with us. Welcome to the new people entering. So the topic of today's webinar is evaluating the potential of aquathermal energy systems. And our speaker, Len Koesemans, will guide us through the do's and don'ts of feasibility studies, focusing on key factors and methodologies. Len is an industrial chemical engineer and project engineer at Extracts, which is a Belgian engineering company specialized in aquathermal energy. And so since 2024, he has been working on sustainability through this technology, aquathermal energy. So he's really our expert of the day. But before I give the floor to Len to dive into the content, I'll just give a quick note on the practicalities. So participants' microphones and cameras are disabled during the presentation, but we will have a Q&A session afterwards around 10:30. So please feel free to drop your questions in the chats throughout the webinars, and we'll address them during the Q&A. Please note that this event is also being recorded and will be shared later and uploaded on our EHPA YouTube channel. So with that, Len, the floor is yours. Thank you.
All right. Thank you for the introduction, Aurelia. Let's see. All right. Indeed, I work as a project engineer at Extract, and Extract is a Belgian engineering and installation company that specializes in aquathermal energy. We use aquathermal energy to accelerate the energy transition, and our vision for the future is one in which at least a significant part of our heating is being done by aquathermal energy. It's not only a hope we've also calculated whether this is a true possibility. And we've recently finished a calculation of the aquathermal potential in Flanders, Belgium. And we've came to the conclusion that 40% of our houses and buildings that are within 1 kilometer of water bodies can actually be supplied with aquathermal heat. And that amounts to about 33 gigawatt hours per year, 33,000 gigawatt hours per year of sustainable heat that we can utilize from our surface water and also wastewater treatment plants. And that is about 15% or 20% of the total heat demand in Flanders. So we truly believe that aquathermal energy is a very important source in the energy transition. And that's also, of course, the reason why we are now working on that for 5 years. To explain a little bit, to provide some context about what aquathermal energy is, I will start with the basics of the technique of aquathermal energy. And basically, aquathermal energy is a source for heat pumps. Heat pumps usually collect heat from the surroundings, which can be, for instance, the air or the ground. But in the case of aquathermal energy, heat pumps collect heat from surface water. And they do that with great efficiency because in general, about 75% of the heat that you need for heating your building when using a heat pump comes from the surroundings, and only 25% comes from electricity. And that electricity is used to both transfer the heat from your source to your building and also to get it on the right temperature. So a very interesting way of heating for the energy transition. Then how we can extract this heat from water bodies depends on the system. So there are typically two kinds of systems that exist. You have the closed systems, in which a heat exchanger is being placed directly into the water body, and an open system in which water is being pumped up from your water body, gets filtered, and runs through a heat exchanger which is on land, and then the water that has been cooled down gets rejected back to the water body. Different systems with different functionalities, with different effects. So the thing with closed systems is, of course, that you create some sort of obstruction in the water body in the form of that heat exchanger, which for big projects can be quite a big obstruction, which can be a downside. Sometimes it's a problem, sometimes it's not. But the biggest, let's say, selling point for closed systems is that there is no filtration needed. Typically, we use closed systems for enclosed water bodies, for instance, lakes, while open systems typically are more used in flowing water bodies. And that is, of course, because the obstruction cost in the water body is much more limited with open systems. But it comes with the downside that filtration is needed, which comes with sometimes higher maintenance costs. And also, you need to monitor your water quality much more in detail than with closed systems. So two different systems, both with their own advantages and disadvantages. In my daily job, I deal with feasibility studies for aquathermal energy projects. And within the WaterWarmth project, we are responsible for work package 1, which actually handles trying to calculate or assess the feasibility of an aquathermal energy project. And I will start now by highlighting 4 key factors which determine the potential of an aquathermal energy project, and then I will go into the methodology we developed to do this assessment. So the first key factor is the environmental impact, which is a quite important one, and the environmental impact is typically in the first place the thermal impact you might have on the water body. The thermal impact, of course, because you take out heat from the water body and supply it to your heat pump, which does decreases the temperature in your water body. And if you have a very big installation and a very small water body, you can have risk of freezing. You can also have a possible impact on biodiversity when lowering the temperature in the water. Of course, in summertime, that can be positive because we see that a lot of surface water, especially in Flanders, they suffer from the formation of microorganisms that are not wanted, that decrease biodiversity, and decreasing the temperature in the water body is actually a positive thing. The thermal impact on the water body is usually limited by regulations, by, for instance, imposing a maximum temperature difference that is caused by the installation in the permitting phase. Other environmental impacts that can happen on the water body or, for example, organism death due to filtration, which is a thing in open systems, of course, not in closed systems. We are following up recent studies that show that actually the organism death is limited to only 30% of what you take from of what you pump up from the river. So it's actually not that big of an impact as previously thought. Of course, you can also have an impact on biodiversity due to leakage of anti-freezing agents with closed systems. But also there we see that usually the impacts are quite limited because most of the times the anti-freezing agent is a very limited amount in comparison with the very large water bodies. Second key factor are technical constraints, which will determine how your installation will look like, and for instance, what if you choose between a closed or an open loop system. Technical constraints can be that there is a limit on the thermal impact you can have on the water body. Of course, that's always important to take into account when building a system. Distance between source and consumer is also a major has also a major impact. Has also a major impact on your project. We see that if the distance is quite large between your water body and your building, for instance, that projects become less feasible. Heat pump readiness, of course, you cannot have aquathermal energy without a heat pump, and if your building or project is not heat pump ready, it makes this technology harder to implement. And also, more and more we see that electric grid connection capacity also becomes a technical constraint for installations, sometimes limiting the peak power you can draw from the grid, or even sometimes making projects impossible. That's not specific to aquathermal energy, but that's more a heat pump issue. Of course, other technical constraints exist, but I will not go more into detail here. Regulatory conditions are the third key factor. And what we've noticed from working in the WaterWarmth project is that these conditions highly depend on your location. We see that, for instance, in Flanders, there is sort of a general rules and regulations, but when you go to France, it really depends in which area you are, which rules exist. So that's sometimes difficult. What we can conclude is that most projects will require permits, either for capturing surface water, for obstructing or using waterways, and also a building permit of some sort in order to build your installation and technical room. And then the fourth key factor is the financial feasibility. And that financial feasibility is determined by the balance between your investment costs, operational costs, and revenues and savings. Those investment costs are determined by the design of your project, the component selection, and you can have some impact on it as well by receiving subsidies, for instance. Operational costs are mainly influenced by the efficiency of your system, which is expressed in the COP, so the coefficient of performance of your heat pump. Of course, very dependent on energy prices, and mainly in the difference between electricity prices and the gas prices in a certain area. And then, of course, you can have other recurring expenses that add to your operational costs. And then, when investing in a project, of course, the most important thing is the revenue and the savings you can have, which are either determined by the reference price of the current installation. When you're investing in an installation for yourself, and heat tariffs when there is an energy company investing in a system and selling heat to customers. In general, we can see that a well-engineered and a well-constructed installation will limit capex and opex and greatly increase the financial feasibility of a project. Okay, and then now to the methodology we've developed with the WaterWarmth consortium. A methodology that starts from a party that does not have that much ideas and they have a heat demand and they want to fill it in with a sustainable source. So the first step there is to get inspired by aquathermal energy, and one way of doing that is by making potential maps and showing areas where aquathermal energy can actually be a main factor in heating of that area. Once someone is inspired, they can do a first check of their project by themselves using the Quickscan tool we've developed with the WaterWarmth consortium, and which is available on our website. Once they've done that first check and no big problems has arisen, they can go on to the third and the fourth step, being a sense check by an aquathermal professional and an in-depth analysis. The sense check, or pre-feasibility study as we call it, we've included this into the flow because we saw that for some projects, the client orders a big feasibility study while there are actually quite soon some discoveries made that make the project impossible. And to prevent clients from making a big commitment to a full in-depth analysis, we've added a step in between that will prevent them from making errors like this. I take for the next slides, I take these two things together. So I will just speak about the feasibility assessment of projects, which is a combination of a pre-feasibility and feasibility steps. And it consists of these 5 steps. So a site visit, a thermal impact study, concept design, permit screening, and financial analysis. So for the first step, the site visit, a site visit, of course, aims to collect data from the building itself, or if it's not a building, if it's a city area, of the city area itself. It collects data like energy consumption, how the building is used, which space is available in the technical room, temperature requirements, or other things. And then, of course, it's also important to take a look at the water body in terms of how deep it is. Does it flow? Does it not flow? Is there a lot of variation in the flow? How does the K-wall look like? Does it have natural banks or kinds of stone K-wall? Is it a metal K-wall? Those things, and also to get an idea of the water quality. These two things, if you don't perform a site visit or don't collect data, will really make the next steps much harder to perform successfully. So the second step in the feasibility study is a thermal impact study. And the thermal impact study tries to calculate what the temperature differences will be caused by the aquathermal installation in the water body. But of course, a water body is not some standalone water buffer, energy buffer of some sort. It has connections with the surroundings. And mainly when the sun is shining, when it's warm outside, your water body will collect heat, which can then be harvested with your aquathermal energy system. So you can take out that heat with your heat pump and supply it to the building. In a thermal impact study, it is therefore important that you get an idea of how this connection with the surrounding works. And also, if you take out heat from a water body, there will exist an equilibrium. So heat taken out will eventually be regenerated again by its surroundings. So when performing a thermal impact study, you try to calculate these things. And on the right, you can see a calculation, a simulation of the temperature differences caused by an open system on a closed water body, where you can see that each building has its own system. And the building in the corner here is the biggest. That's why you see the darkest color. But you see that at this specific moment of the simulation, the building creates a temperature difference of 1.5 degrees in the water body, which is okay, it's limited. Here on the left, you can see the simulations of the flow caused by pumping up and rejecting water from that water body. So these are things we typically do in a thermal impact study to calculate whether the installation will cause a problematic decrease in temperature or not. That was an example for standing water bodies. This is it's also possible on flowing water bodies, where here you have the point where you reject the water that has been cooled down by your aquathermal heat exchanger. All right, so it's important that the thermal impact study is not just a static calculation. We usually make a digital twin of the water body. We do 3D mapping of that water body, and we perform dynamic simulations to calculate the effects of our installation on the water body. Very important in that is to also calculate the interaction with the environment, because that has a very big effect on the potential of your project. If you don't take that into account, you probably underestimate the potential of your water body. What I also would like to stress is that it's important to use accurate data if they are available to use measurements, and if not available, then public data that is as accurate as possible. For our models, we use the flow, the depth of the water body, the relative temperature without the aquathermal energy installation, and weather data that will, of course, tell you something about the interactions with the environment. The next step in the feasibility study is a concept design, where you will typically make a first sketch of how the project would look like. So a technical sketch, which dependent on the project, can be very detailed or can be something more general. But usually you also add a component list with this sketch and some component requirements. For these component requirements, it's very important to have an idea about the water quality, because it has a big impact on how you should choose your components and what your components should be capable of. And these water quality measurements, we usually recommend to measure 3 parameters continuously. That's the depth, the turbidity, and the temperature. And then also to do some lab analysis, take some samples and analyze them in the lab. And then we look at particle size and distribution of suspended solids, the concentration of those suspended solids, the acidity and the chlorine concentrations for the to get an idea how salty the water is, and also algae presence or other biomaterial. And that will determine which components we select and how the components need to perform. Then next step in the feasibility study is permit screening, which is sometimes overlooked, but is actually rather important. What we usually aim for in the permit screening is to receive a pre-agreement from the authorities for the project already during the feasibility phase. So it's not really getting the permit directly, but yeah, to have a good idea that when you would file the permit, that it would be accepted. And of course, it's important because the demands of the permitting authority should be incorporated in the concept design. What we usually do is that we start to have conversations with authorities during the project, usually after we have done the thermal analysis and a concept design. We involve them quite soon. We talk with them about the project, and then usually we have to do some iterations based on their comments, and then we can present it to them again. In that way, by involving them, we get we get a good sense whether it is permittable or not. Sometimes we came to the conclusion that they were not interested in giving permits, and we had to redesign a system completely. But other times they agreed from first concept design. So. And then the final step of your feasibility study, and for some this will be the most important step, is the financial analysis, which starts with a calculation of all the costs your project will have. So the operational costs, as previously mentioned, mostly determined by your concept design and your component selection. What we usually try to do in these feasibility studies is to get price offers from manufacturers already in this stage, based on our concept design, which will not mean that the project in the end will look exactly like how we've designed it, but it gives a much better understanding of what the possible costs can be than just doing a calculation based on let's say reference projects or euros per kilowatt figures. So once you have the capex, so the investment costs, you can try to estimate the operational costs, and operational costs consists, well, most of the times, for the biggest part, on maintenance and electricity consumption. Depending on the project, insurance can also be something that you want to take into account. An administrative fee, it can really become complex when you work with multiple sources or with district heating grids and everything. So operational expenses, calculating them correctly is of course very important for assessing the financial feasibility. And then the reinvestment costs. Reinvestment costs being an estimation of the reinvestment that is required in a project. Of course, in real time, once you're operational, reinvestments can happen because components fail and need to be replaced. That will not happen on a yearly basis. Of course, sometimes you will have years with smooth operations, and then sometimes you'll have years where you have to reinvest quite a lot. But it's of course difficult to predict, and that's why we calculate the repacks, and we do that by actually calculating the investment cost of components and dividing them by the expected lifetime. For instance, if you have a component of 100,000 euros that is expected to be replaced after 20 years, then your reinvestment cost becomes that 100,000 divided by 20 years, and that's 5,000 euros per year of reinvestment costs. For someone that is operating a system, this is interesting to know because it gives you an idea of how much money you have to put aside to reserve for reinvestments. Step 2 of the financial analysis is calculating your revenues and or savings. Revenues, especially when you are an energy company investing in these projects, and savings when you're building an installation for yourself. Once you have your costs and your income, revenue or savings, you can calculate some financial parameters, which I've listed here. Total cost of ownership being the first, and with total cost of ownership, we calculate all the costs, sum them up over a certain time of year, a certain time. So in this example, on 30 years, we check what all the costs are and we add them up. And then it gives you an idea of how the project, as you envisioned it, how much it will cost, and you can compare it to other scenarios or to a reference scenario, the current scenario, for instance. In the example on the right, you see an aquathermal installation that has been designed on peak load, so which can carry the full load of heat demand. One that has been calculated on partial load, so which can actually provide 80% of the heat demand over a year, which comes with lower investment costs and lower reinvestment costs because the installation is smaller. And then reference installation, which is a fossil gas boiler. And here you can see it gives perfect clarity to someone investing which will be the most cost-effective solution. The same is true for the next parameter, which is the levelized cost of heat, and that's actually just the total cost of ownership over a certain amount of years divided by the energy that is being produced by that installation over that same time period. It's just another way of calculating the costs, the total costs of your project. And then you have the internal investment rate and the return on investment. The internal investment rate, it tells you something about the profitability of your investment, and the return on investment about how much money you will be able to earn in the long run with a certain investment. What we typically see with aquathermal energy projects is that internal investment, well, it's actually with heat projects in general, they have long payback periods. Investment rates are certainly not always double digits, and return on investment is usually also limited. Usually when we calculate this, we do this for a certain amount of years, and that's usually 25 or 30 years with these kind of installations. But yeah, we can also express it the way you see in these two graphs, where on the x-axis you see the years of operation. This can tell you something about how much years you should be in operation to receive certain amount of profitability of your project. And then the fifth parameter is the net present value. I'm not going to go too much into detail there, but that's actually the total cost of ownership, but it takes into account the devaluation of money over time. Once you've calculated these final parameters, you can do a sensitivity analysis, and a sensitivity analysis aims to change some key assumptions in your calculations and see which effects they have on the financial parameters. And in that way, you can see which things should be guarded, which costs, for instance, should be guarded closely, because they might have a big impact on your project. And step 5 can be a scenario comparison where you calculate different scenarios, different energy sources, different options for investing in renewable energy. All right. So this was an overview of the feasibility assessment of the aquathermal energy projects. If you want to read more about this within the WaterWarmth project, we have made 2 product sheets which are available on our website, one for pre-feasibility study and one for feasibility study. There you will be able to read some more details about how to perform these feasibility studies. It was also our aim to make these product sheets and that other parties could then base their tender for studies on these documents, so that in the end we reach more successful feasibility studies and more thorough feasibility studies, which provide clients with the right answers. I guess we have some time left for questions. So if you haven't already, you can pose your questions in the Q&A section.
Yes,
I see two for the moment.
Yeah, if I can assist, indeed. I see 3 questions so far. David is wondering if you have a recommendation for a minimum source temperature, and would you recommend electrical heat backup systems are included in the overall specification?
A minimum temperature, we usually say that with closed loop systems, there is no minimal temperature of your water body because they can function even when the top of your water body has frozen over. But for open systems, of course, it's a different scenario. It's a different case. You need to pump up something. You need to cool down what you've pumped up, and in order to prevent freezing before rejecting it, we say usually that the temperature should be 4 degrees of your water body. If it drops below 4 degrees, you have to change to a backup system. But that also depends on the temperature difference between the incoming and outgoing flow. So sometimes you will have projects that have a temperature difference of 5 degrees, and then of course you will need a 6 degree minimum in your water body to be able to still supply aquathermal heating. And then as to electrical backup systems, it's possible. You only have to take into account that your electric connection might become a whole lot bigger than what you've previously designed. Usually in bigger projects, we see that we provide backup and top up with other heat pump systems, for instance, air sourced or ground sourced.
Okay, thank you. I think that you also see the 2 questions from Ben. The first question is, can you comment on biofouling issues for both open and closed systems? For open systems, it is usually necessary to use a continuous dose of bioseed to keep exchanger surfaces clean enough. That's the first one.
Yeah. Biofouling can be an issue. It really depends on the type of water. We usually see that the issue is bigger in more salty water bodies. Of course, when we design a system, especially an open loop system, we try to incorporate a way of getting rid of your biofilm. For a heat exchanger, that can be done chemically, but we try not to. As it can also be solved mechanically by increasing the flow rate in some plates to flush them, and therefore flushing the biofouling out. A continuous dose of biocide is absolutely not recommended, because it would mean that you will reject it back into the river as well, and that is usually not permittable. We know that by providing a way of cleaning your heat exchanger and cleaning your pipes, that you can keep it under control. And as to the closed systems, usually it's not that big of an issue. What we see in the systems that we have ourselves in operation, we usually take them out about once every 5 years to clean them, and that's enough to guarantee good functionality.
Okay, thank you. And then the third question, also from Ben. In a closed system, is it necessary to have the exchanger coil close to the surface when warmest water is available?
Yeah, the placement of your heat exchanger is important, of course, but it's actually the other way around. In winter, usually the bottom of water surface is warmer than the top. Most of the times we won't really look into that too much because the difference is not usually significant. It only is significant with depths of, let's say, 4, 5, 6 meters. If your water body is between 1 and 3 meters of depth, it doesn't really matter where you place it exactly. But yeah, it has maybe a small impact. What we also usually advise is not to place it very close to the surface because when in winter time it starts freezing, you want to prevent your heat exchanger being in the zone of freezing because it can damage your heat exchanger. So that's why we usually place it just on the bottom, and it's perfectly fine there.
Okay. Is there any other questions in the audience? I don't see any. I hope that Len answered the questions. Okay, so I guess that we can now close this webinar. So thanks a lot, Len, for your presentation. Also, thanks to everyone for attending. As mentioned earlier, this session has been recorded. We'll later we'll upload it to EHPA's YouTube channel. We'll also publish a recap article on the EHPA website together with the slides. And then before we close, I'd also like to invite you to join the final webinar of the WaterWarmth series next Monday on 8th of June at 2 p.m. Because the project is slowly coming to an end, and we will host one final session focusing on lessons learned, practical experiences from pilot cases, and future pathways to scale up aquathermal energy solutions across Europe. So my colleague Francesca has just shared the registration link in the chat. And yeah, so we hope that we see you very soon again. And that's it. Bye-bye, everyone, and see you.
Bye. Thank you.